All right. Hey guys, it's good to see everyone again. Today, what we're going to be doing is looking at metallic bonding. So we've already had a look at covalent and ionic bonding. So this is the last real kind of bonding that we're going to have to cover over the course of this material. It's a little bit different from some of the other bonding that we've come across before. Metallic bonding has a few idiosyncrasies. There's things that make it very, very different to the sharing of electrons in covalent bonding and that kind of ripping away of electrons in ionic bonding. And so metallic bonding is very, very different to those things. Now, obviously, covalent bonding, when we did covalent bonding, we just go over what that was. It's a sharing of electrons, and it's between non-metals and non-metal atoms. Ionic bonding that's when you gain or lose electrons. So the atoms become charged and therefore they attract each other. So these guys, the covalent molecules, are staying together because those electrons are shared and they're kind of like just bound together in this bond. And ionic bonding, the atoms are stuck together because one of them's lost an electron, one of them's gained an electron, and that charge is now making them stick together through the static electricity force, the electrostatic force. And for this one to work, you have to have one metal and a non-metal. So you've got to have a metal non-metal. For metallic bonding, this is metal positive ions surrounded by delocalized electrons. And for this one, it has to be only metals. You must be no non-metals in metallic bonding. This one's the easiest one to remember because obviously metallic bonding means metals. You're going to be using metals. So please remember that because it's incredibly important. All right. How do I clear everything? I'll just scroll up. So, what we're going to do then is sort of have a look at how metallic bonding appears first of all. So let's do a really simple example. Let's go with sodium. If you look at your periodic table, you'll see that sodium is element number 11. It's got an 11 for its atomic number, and that means that it has 11 electrons. So as we know, in the first shell we're going to have 2 electrons. In the second shell we can fit 8 electrons. That will bring us to 10. Sodium has 11 electrons, so it needs one more electron in this shell here. There we go. Getting much better using this stylus to draw my shells. So when we create an ion, if you remember, what happens is that we either lose or gain electrons. In this thing here, you'll see that this electron is all by itself. And so to form an ion, this electron will fly away. So we'll lose one electron. And so then what will we get? Well, we'll have a sodium ion, which will look something like this. It'll have 2 electrons in the outside and then 8 electrons on the outside there. So this is what we'd get. We'd get a sodium 1+ ion. So this square brackets means it's everything is plus. And then I'm also going to have one free electron. We've got one electron here, this extra electron that sort of came from over here. Right. So this is all well and good. We know this from ionic bonding. But in ionic bonding, there are negative particles to take this extra electron. So this extra electron would go somewhere. Moves to negative ion. But in metallic bonding, that doesn't happen. In metallic bonding, there's no negative place for it to go. So we're stuck with this extra electron. So what this means is in the same area, so I'm just going to draw this a lot of atoms now. So in the same area, if I was to zoom into the atoms in a metal, all of these particles would be positively charged. So we'd have lots of positively charged particles. All metal atoms in the metal are positive metal ions. They've all lost electrons. But where have those electrons gone? There's nowhere for them to jump to. So in fact, they actually just stay around the ion. But they're no longer stuck in the atom. They're free to move wherever they want. The electron that was here, this electron that was here, is now free to move anywhere it wants. It can go over here, it can go over here, it can jump around here, it can go over here. These are free to move electrons. They can go wherever they want. They can move about anywhere in this whole area. So we call this a C of delocalized electrons. This word delocalized means that they're not stuck around an atom anymore. They can go wherever they want. And this idea of lots of positively charged particles held together by negative electrons gives us a lot of the properties, explains a lot of the properties that metals actually have. So, let's have a look at some of the properties of metals and think how this structure that we've described here of what a metal looks like is explaining what the property actually is. So, I think one of the biggest things we've got, one of the most, the most common one that we know about metals is that they're shiny. Why are they shiny? That's really simple. They're shiny because they reflect light. That's all you need to know at this level. There is a reason for it, but it's way beyond the scope of the GCSE. Right, let's move on to the next one, which is being malleable. Now, if you remember from Key Stage 3, malleable means that it can be bent or shaped. I'm sure you know this if you've ever taken a piece of aluminium foil and you've scrunched it up into a little ball. Metals are very, very easy to bend and shape into different shapes. That's why we use them for things like saucepans and carbonets. These really complicated shapes that things need to be bent and hammered into. You may not think of metals as being easy to bend because a lot of the times that you use them, like in a knife or something, it's relatively difficult to bend that steel. But if it's warmed and hammered, then you can get metals to be bent into pretty much any shape you want. So let's try and explain why this is the case, why this happens. So, imagine we've got our metal atoms like this. Here's my metal. All these positive ions stuck together like this. And if you remember, what's surrounding those atoms, these ions even, positive ions, is that sea of negative electrons. So we've got sea of electrons, and here we've got positive ions. Right. If I apply a force here, so I'm going to apply a force to this row of atoms there, that's going to make the atoms slide over the other atoms that don't have that force applied to them. So what we'd get is, if we did this, my bottom row would be untouched. But this row would slide over. Now, in most substances, if you were to do this with the atoms, it would just shatter and break. So what happens in non-metals, if you've ever tried to bend a pencil and it breaks into two, it's because the atoms are being forced away from each other and they'll just break. That's what should happen in this situation. But because of this sea of delocalized electrons, those electrons move with the atoms and hold it together. So the sea of electrons, oh my gosh, the sea of electrons moves with the ions. And that is why you can bend metals into different shapes, because the sea of electrons still holds the atoms together, because the sea of electrons moves with the positive ions. Alright, let's move on. Let's go to being high density. So, high density. Oh, pen. Now, density is a bit like saying that this is heavy, like metals are relatively heavy. But we shouldn't use the word heavy, because think about it. A penny is made of metal, but a tree is made of wood. Which is heavier? Obviously the tree. But would you consider metal or wood to be lighter? Well, I'd consider wood to be much lighter. So it's not just about what the material is, but it's also about how much of the material you have. And so density is a way of describing that. Density is, just for a maths equation, is its mass divided by the volume equals density. So we're looking at how heavy it is, but also how much we've got. Now, if I had the same amount of wood and the same amount of metal, the metal would be much, much heavier. And this is because they've got a really high density. So let's have a look why that's the case. Now, metals have a high density because the atoms are packed very closely together with the electrostatic force. Ooh. Electrostatic force. Now, what is this electrostatic force? Well, if you remember, if I have something positive and something negative, those two particles are going to want to move together. We call this force the electrostatic force. Now, in my metallic bond, obviously I've got loads and loads and loads of positive atoms like this. In my metal, there's my positive atoms, and we said already that there's this sea of delocalized electrons around them, like this. Well, those delocalized electrons are negative. And so the negative charge of the electrons, negative charge of electrons, attracts the positive charge of the ions. Because this negative charge here attracts the positive charge of the ions, that means all of those positive charges stick together. So they pack really, really closely together, and that means that metals have a very, very high density. All right. Another thing we need to talk about is why they have a high melting and boiling point. If it's got a high melting and boiling point, what is it going to? Why do these things have a high melting and boiling point? Well, it's also to do with this here. It's also to do with this, the positive charge, the electrostatic force between the particles and the electrons and the positive ions. That's why it has a high melting and boiling point. To get something to melt or boil, you have to provide energy. The energy needed to separate the positive ions from the negative electrons is very high. Because the electrostatic force, is so strong. Basically, because the force here between the positive ions and the negative electrons is so strong, it's really difficult to break those atoms apart. It's like they're stuck together with magnets in between them. And so pulling them away from each other is very difficult because they want to be closer together. They want to be packed really close together. So because the electrostatic force is so strong, these metals most of them have high melting and boiling points. All right, let's also talk about the strength, because that's also to do with this as well. Again, because the electrostatic force is so strong, metals are difficult to break. So therefore they have a really high strength. Again, all because this electrostatic force here, the force between the negative electrons and the positive ions is so strong that it's really difficult for those electrostatic forces to break. And so therefore it's got a really high strength. All right, last one we're going to do today is its conduction of electricity. So last thing that we're going to do is conductor of electricity. Now, for a conductor of electricity, we've got to think, what is electricity first? So let's define electricity. electricity is a movement of charge. Now, can you think of anything that is charged and free to move in my metal whilst I draw this? So think about that structure of a metal. Is there anything here that's charged and free to move when I draw out my metal? So here we've got our fixed positive ions. And what are they surrounded by? That's right. They're surrounded by a sea of delocalized electrons. And delocalized means they're free to move around. And electrons are negatively charged. So they've got movement and they've got charge. So basically, if I've got an electron here and I put some electricity into it, that will make the electron start to move across my thing. And this is why we make wires out of metal, because the electrons that are in the metals are free to move, and that means they'll conduct electricity. So, metals contain free, delocalized electrons which means they are free to move and conduct electricity. All right. That's it for today, guys. Please have a go at all the questions that I set for you. A few people have been missing out some of the questions, so please do try all of them. And they will go back over the other types of bonding, because you can't forget the ionic and the covalent bonding either. So I'm going to ask some questions about comparing metallic bonding, ionic bonding, covalent bonding. So it's really good to go back over some of those ones, and I'll put the links on to the C6, C7, the C5, C6, C7 topics if you need to go back over them. They're all on the chemistry tab in Teams. All right. Thank you very much, guys. Have a great day.